All right, these are the first notes for chapter 2. So we're looking at section 2.1. We're talking about the rectangular coordinate system and various graphs that we could plot on the Cartesian coordinate system. So just first a mention about notation. So often when you see something like 2 comma 4, it's always sort of a reference to a set of xy coordinates. So it would represent, the point which has an x coordinate of 2 and a y coordinate of 4. But we saw in previous chapter that we saw often we'll write a solution set, looking like this, right? So it's the x value such that x is between 2 and 4 exclusive, and we would draw it on a number line like this, but we would write it sometimes like this as well. All right. So, it shouldn't generally be a problem for us because we'll know from the context of the problem whether we are talking about a solution set, in this case non-inclusive of the endpoints, or if we're talking about an ordered pair. And in this section, things like this will represent an ordered pair because we're talking about graphs, right, instead of solution sets. All right, so please make sure that you look and read pages 184 to 185 in our textbooks, and this will give you a better full description of some history of ordered pairs and the development of the Cartesian coordinate system. All right, let's start with the distance formula. The distance formula is this, but we can derive it if we look at the Pythagorean theorem. So here's a segment, and we want to know its distance. I called it d. It would be like the Pythagorean theorem. We would generally call that the hypotenuse, and we would call that c. So I'm looking at the distance between these 2 points, but I'm breaking it up into the distance along the x direction and the distance along the y direction. So that creates this right triangle where the 2 legs of the right triangle are a and b, and the hypotenuse is the actual distance that we're trying to calculate, and we'll call that d. So we're using d squared rather than c squared here. But if we think about what's a is simply the difference in the x coordinates, so it's x sub 2 minus x sub 1, and then b, the way we've set it up, is the difference in the y coordinates, so y2 minus y1. Ultimately, this formula is fairly forgiving because if I were to reverse this x1 and x2, generally that'll give me a sign change, but we're squaring it, so it doesn't really matter. So if you say x sub 1 minus x sub 2 or x sub 2 minus x sub 1, doesn't really matter. And who's to say which one is x sub 1? Maybe this is the second point. Maybe this is the first point. Really doesn't matter. So it's a very forgiving formula. So we take the difference in the x's and we square it. And we add to it the difference in the y's squared. And then we square root it to get rid of the 2 that was over here on the d. We square root both sides. All right. And yes, when we take the square root of both sides, we generally want to consider the positive and negative roots. But in this case, distances are only positive. So we don't have to worry about, when we take the square root of both sides, worrying about the positive and the negative. All right. So we want to find the distance between these 2 points. Use your distance formula. Pause the video. Do that. And then I will show you the answer. All right, so d is equal to, and then we will do the square root, and now it's the difference in the x's, and again, it doesn't matter which one goes first, so I'll say 3 minus a negative 2, which is plus 2, quantity squared, plus negative 5 minus 8, quantity squared. All right, and so then that's equal to, all right, that's 5, and 5 squared is 25. And that's going to be negative 13, but negative 13 squared is 169. And that is the square root, when we add that up, of 194. Okay? And 194, I don't think anything can be done with 194. Let me just see. 194, yeah, I divided it by 2. 194 is 97 times 2, so clearly there's no perfect square. 97, 97 is prime, and so we cannot simplify anything else. Okay. All right. The next thing, converse of the Pythagorean theorem. So the Pythagorean theorem says if you have a right triangle, then this relationship among the lengths of the three sides is going to be true. The converse says if three sides of a triangle have this relationship, their lengths have that relationship, then we can prove the triangle is a right triangle. So it's a way of proving the triangle right. So what we want to do is we have three vertices. We want to know, are these the vertices of a right triangle? So now we don't want to graph it. We want to do it algebraically. So we'll look for the distance, right? Is the distance between these two, RS, the distance between ST, and the distance between RT. And so we'll use the distance formula for those. So now what we really want to think about is, well, can we tell right now which one of these lengths is going to be the hypotenuse? And the answer is no. But the hypotenuse, if there is a hypotenuse, right, we only call it a hypotenuse if it's a right triangle, and we haven't determined whether it's a right triangle. But if there is a hypotenuse, it would have to be the longest side. So let's try, let's start with, I'm going to call it D, distance, and then a subscript RS. So the distance between RS, we could just call this RS like that. You know, in geometry, I think we use this symbol to mean, actually, do we do that? Or do we do, I guess we just say RS in geometry, which represents the length of the side. I guess the signal up above means that it's segment, and this means the length of the segment. So either way you want to do it. And then, so we do square root of, and so we want to say the distance between, the difference between the x's, that's 5, and squared, that's 25. Plus, and then the difference in the y's, that's going to be 3, so square that, and that's 9. And so that is the square root of 34. Okay, and now let's try st, or if we want to say the distance and then subscript st, either one. So that is the square root of, and we want to look at the difference in the x's between s and t, and that's going to be 9 squared is 81, plus the difference in the y's between s and t, and that's going to be 2 squared is 4. And so that's going to be the square root of 85. And for this particular problem, it makes sense for what we're going to do when we're finished with the third one. Don't try to simplify these. I don't think these do simplify, but even if they did, don't simplify these. So if this was square root of 20, don't turn it into 2 square roots of 5. Leave it, and it'll make sense why we do that in a second. Okay, and then the last one would be TR, or again, RT, doesn't matter which way you put those, D, and then let's say TR. All right, and so that one is going to be the difference in the x's, which would be 4 or negative 4, depending which way you do it, but squared is 16, plus, and then the difference in these two y's, that's going to be 5, and squared, that's 25. All right, and so that is the square root of 41. All right, so now what we want to do is we take these things and we put them into this formula and see if it's true, right? We have to check to see if a squared plus b squared is equal to c squared. So the bigger one is 85, so that's clearly going to be the c. And so we square them. So let's just call this one a, so that squared is 34, plus 41, is that equal to 85? And you can see that's equal to 75. So 75 is not equal to 85. So it's not equal. So therefore, no, there's no right triangle. Not a right triangle. So no. Okay. And then you can see why it was, good not to simplify. None of these did simplify, but if they did, you would not want to. Because squaring, like if I did square root of 20 and I changed that to 2 square roots of 5, which is easier to square, this or to square this? Clearly, it's easier to square this. This, you'd have to say, okay, 2 times 2, that's 4 times the 5. So it's just simpler to just say, well, this squared is 20, right? It's just a little bit faster. All right. So the collinearity theorem. So 3 points are collinear if the sum of the distance between two pairs of points is equal to the distance between the remaining pair of points. Okay, so what that means is, let's say I have 3 points. Let's call it X, Y, and Z. All right. So these 3 points are going to be collinear if the distance between this plus this is the distance between these two. And so clearly this would not be collinear because this distance is shorter. If you remember from geometry, a triangle always has the largest side has to be smaller than the sum of the other two. And so if Z was on this line, so if Z was out here somewhere, then you can see that this xy plus yz would be equal to xz, and so now we know they're linear if the two add up to if the two smaller ones add up to the same length as the distance, the larger distance between the two. So what we have to do is just figure out what are the distances, and then do they add up? All right, and if they're not, if they don't add up, then it's going to be something, the longer side is now not the sum of the other two, so that means it would form a shorter distance, and it would be a triangle. Okay, so let's just find these distances. This time let's just call it AB. All right, so AB is the distance. That's going to be -2 squared, which is 4. And then the difference in the y's, and the difference in the y's is going to be 2, and that's squared, and that's 4. And so this is equal to square root of 8. And we'll leave that for now. We're probably not going to use the Pythagorean theorem, so probably we'll want to simplify that, and we're not going to square these. We're not looking for, we're not putting it in. We're not checking for a right triangle here. So probably 2 square roots of 2 would be better in this case. All right, and then let's do BC. And so BC, the distance between the x's is 8, squared is 64. And add that to the difference in the y's, and that's also 8, squared is 64. All right, and so that is the square root of 128. And then 64 goes into that. 64 comes out as an 8, square root of 2. All right, so at least we'll be able to add these. It looks like the radicands are the same. We could add or subtract these as necessary. And then let's do CA. And that's the difference in these x's. That's 10, squared is 100. And then the difference in the y's, that's also 10, and squared, that's 100. Okay, and so that is the square root of 200. And then clearly you can see that 100 is a factor in there. We can bring that out as a 10, square root of 2. All right, so now do the two smallest add up to the largest? And sure they do. So adding these two up, that gives us 10 square roots of 2. And so that's the same. So it's got to be this situation where the two pieces, this is 2 square roots of 2. And this is 8 square roots of 2, not drawn to scale, obviously. And the distance between the two outer ones is going to be 10 square root of 2. So yes, they are linear. The 3 points are linear points. Okay? All right, let's go on now to the back page. All right, so the next formula we're going to talk about is the midpoint formula. So this is, if I have the endpoints, and we're calling the endpoints x, x1, we're going to call them out as x sub 1, y sub 1, and x sub 2, y sub 2. So if we have those, this formula will give us the location of that midpoint. Okay, so it's really a pretty simple formula. It's simply the average of the x's. So if you think about like, okay, how do I find this point? It's halfway in the horizontal direction, and it's halfway in the vertical direction. So it's the average of the x's and the average of the y coordinates. All right, so find the midpoint of a segment with the following. So what I like to do is not do it all at once, but like do x for the midpoint is equal to, and then I do the two x coordinates, so -7 plus a -2 over 2. And so that would be, let's put down here, -9/2. Okay. And then the y coordinate for the midpoint, that's the sum of the y's, so that's -5 plus 13 over 2. And that's going to be 8 over 2, 8 over 2, which is just 4. And so then I'll write, okay, the midpoint, M, is located at -9/2, comma 4. And so that is the location of the midpoint. Okay. Now this one's a little different. Segment PQ, so let's kind of I'm just going to draw it. It's not going to be to scale, but it's just a visual to help us see what's going on. So P and Q, and it has a midpoint that we're calling M. And this time I'm given the location of M and P, but I'm not given the location of Q, and so we got to work sort of backwards. And so again, instead of using the formula like this, break it up separately. So we have the midpoint x equals the I'm going to change that differently. The x coordinate of the midpoint. So I want to say x point of the midpoint. The x coordinate is the x for P plus the x for Q over 2. All right, and so what we really want to do is just plug in the points, right? So we know the x coordinate of the midpoint that's given to us, that's 4, is equal to the x coordinate for P, that's 8, and we don't know the x coordinate of Q over 2, and so we just want to solve this for Q. So we multiply both sides by 2, we get 8 equals 8 plus x coordinate of Q. So I think you can see the x coordinate of Q is going to be 0. X coordinate of Q is 0. And then we'll do the same thing for the y. Okay, so the y coordinate of the midpoint is equal to the y coordinate for P plus the y coordinate of Q divided by 2. And so we'll plug in what we know. Y coordinate of the midpoint is -4. Y coordinate for P is -20, plus the y coordinate of Q is what we're looking for, divided by 2. All right, so we're going to multiply both sides by 2. We get -8 equals -20 plus the y coordinate of Q. Add 20 to both sides, so the y coordinate of Q is going to end up equaling 12. So then let's rewrite it. So say point Q is 0, 12. Okay. But so don't try to do this all at once. You want to sort of set up a separate equation for the x's and a separate equation for the y's. Okay, the y coordinates. All right. Total revenue of full-service restaurants in the United States increased from 124 billion in 2009 to 137.4 billion in 2013. Use the midpoint formula to establish the total revenue for 2011. So notice 2011 is halfway between, right? So we have, if we have like a graph here, and we have a particular value for 2009, and it's here, and then we have 2013. 2013 is here, and we have that values up here. Halfway between here is 2011, and so we want to figure out what is the midpoint. So that we know the x coordinate that's going to give us there, so it's going to have to be the midpoint of that line, if that kind of makes sense. We're going to estimate that the change is continuous, right? It's constant, and so it's going to be a line is what we've got to sort of estimate here. So use the midpoint formula to estimate that. So we know we really just need to find the y coordinate of the midpoint, really. We know that 2011 is midway between, so we just really need to find the y coordinate of the midpoint, and that we know these two y coordinates for 2009 and 2013, so find the midpoint of that. So simply plug those in: 124.0 plus 137.4, and we simply divide that by 2. All right, so that's 261.4 divided by 2, or about 130.7 billion dollars. Okay. All right, let's look at some graphs now. Equations in 2 variables now. The solutions of these types of equations will be any point x, y that satisfies the equation. So we have an equation, and we solved equations before, but the equations before had only one variable. So we would solve for the x. And so sometimes the x had more than one value. Here, though, the solution to this is just going to be the graph, like a line or a curve of some sort. Okay. And so we want to find at least 3 pairs of coordinates that will help us graph this. And so I've given you a table. Probably, what's good is if you just pick some x values. So let's try -1, 0, 1, and 2. I know that's 4, but it says at least 3. So let's plug in. So we plug in the x of -1 there. And that ends up with a 7. So that means I plot that point. So I have -1, and then 1, 2, 3, 4, 5, 6, 7 up here. Okay. So 1, just 1 right outside. And then 0, plug a 0 in. Well, that gives me a 5. And so at 0, I'm at 1, 2, 3, 4, 5. Make that dot kind of big because it's hard to see on that thicker axis line. And then when I plug a 1 in, that gives me a 3. So 1 and then 1, 2, 3. And I think we can kind of see, right? And hopefully you remember lines, right? We could just start with the y-intercept 5, and then do a slope of -2. So I go down 2 over 1, down 2 over 1, down 2 over 1, and so on. So you could sort of just fill the space with dots and then draw in this case, a line. And it's good to put arrows on the end to show that they don't just stop, it goes on forever. Okay? All right, now the next one's a little bit more challenging. It's not really a line. It's going to be a curve. And so let's do this. Let's go ahead and just assume we're going to do the same thing. Let's put some values in. So we're starting at -2, -1, 0, 1, and 2. And let's see which one of these makes, if any of these make sense. So if x, now this is weird because we're putting x over here, and then we solve for y, right? Because we put in the x is the input, y is the output universally, right? So, like here, that's the independent and that's the dependent. So we put in x, we get out y. So in this case, if I put a -2 in for x, -2 equals the square root of y minus 1. So is that even possible, right? Can I get from this side, can I get a negative out of this thing? And the answer is no. I can't get a negative out of a square root. Remember that when we take the square root of both sides of an equation, then yes, we take the plus or minus, but the radical's there. We didn't take the square root of both sides. The square root was already there. It's only the positive root, not the negative. So we could never get a negative out. So this doesn't make any sense. I would never be able to plug an x value of 2 in there, of -2, sorry. And the same thing for -1, right? Can I plug a 0 in? Let's try. So I put a 0 equals the square root of y minus 1. So we could, in this case, yes, we could get a 0 out of this. How would we get a 0? Well, this would have to be 0, right? And then the square root of 0 is 0. So that means y would have to be, why did I cross that out? Y would have to be 1. Okay? And then what if it was 1? That means this whole thing would have to be equal to 1. That means the stuff in here would have to be equal to 1. And so that means that y would have to be 2. And let's plot these points too. So 0, 1, we're here. And then at 1, we're at 2. And then at 2, we haven't done that one yet. So now let's say it's 2. All right, so how would this whole thing be equal to 2? Well, we could square both sides and get 4 is equal to y minus 1. And then, of course, add 1 to both sides. So we get 5. All right, so we have 2, and then we go up 1, 2, 3, 4, 5. And so it's a curve. It's actually half of a parabola. All right. Now, the problem, you have to be careful. Like if you took this equation and you said, well, let's square both sides. So we get x squared is equal to y minus 1, and then we could add 1 to both sides. So y equals x squared plus 1. But the problem is we have some limitations. What we did is we squared both sides to get this, and then eventually we kind of rewrote it so it looks like this. That is, if you remember from Algebra 1, a quadratic equation, a quadratic function, if you will, and it's going to give us a parabola. But we have some limitations in the way they gave us this problem, because we know we have some limitations on the x values. X cannot be negative in the original one, but here negatives are okay. So if we were to ask to graph this thing, then we would have the other side of this parabola as well. But we don't here because of limitations on the way they gave us this equation. All right, x cannot take on negative values. So it's only the 0 and above. The negatives are no good. Okay. All right, so this looks a little bit like what we've got here. So in this case, let's do -2, -1, 0, 1, and 2. And now x's can be negative. So pause the video and fill these in and plot your graph. Okay, so now with a -2 in here, -2 is squared, that's 4. And then it's -4 though. Remember that this is not negative of x squared, right? This negative is not going away in the squaring. So this -2 does not counteract with that negative and make a positive. All right, so we have the negative of -2 squared, right? This negative is outside the parentheses, it's here. So this will give us a 4, but it'll be -4. So -4 plus 2, that's -2. All right, so we have, let's plot that point at -2. We're down here at -2. Okay, and so let's try -1. So I plug a -1 in here. That's going to be a +1. All right, so at -1, we're at +1. 0, that's easy. That's just going to give us 2. So at 0, we're up here at 2. And then at 1, 1 squared. So you can see there's a repeat here, right? 1 and then -2. There's a symmetry about this as well, you might think. And so this would be here. Okay, and so that is like an upside down parabola. Okay, and we put arrows on it to indicate that it kind of continues. All right, the last thing we want to talk about is intercepts. So we find the y-intercept by putting x value of 0 in. So think about that. So where are the coordinates? Where are the points that have x coordinate of 0? They're all on this line, right? So that would be the y coordinate. So wherever that graph crosses the y-axis, that is the y-intercept. So put a 0 in to the equation, figure out what the y is. That will give us the y-intercept. And then the reverse, if we want the x-intercept, we put a 0 in for the y. So if you think about all the points on this x-axis have a y coordinate of 0. So if we want to see where a particular line crosses the x-axis this time, or find the x-intercept, we put a 0 in the equation for y, and then we solve that for x. Okay, so this is the homework for section 2.1, and it is due next class.